Hi, this video is on Module 8 for Math 125. Module 8 covers sections 10.7 and 10.8, which are both on probability. And you're probably thinking, well, we did probability in Module 7, which we did, but this is going to be just more probability, some more complex probability problems. So before I jump in, I just want to talk about the type of answers that Connect is going to ask for. So Connect, in a lot of these problems, asked you to put your answer in reduced fractions. So let's talk about that just for a minute. So if you have a fraction, let's say 8 over 10, you have two options to reduce it. You can reduce it by hand, and if you want to reduce it by hand, you're just going to look at both numbers and find a common factor. So what number goes into 8 and 10? You could divide both of those numbers by 2, okay? And by doing that, you're going to get a 4 on the top and a 5 on the bottom. So 4/5 would be the reduced fraction of 8 over 10, okay? I'll give you another example where maybe we have some other options in terms of factors. So take the fraction 8 over 16. 8 over 16 have several common factors. So 2 goes into both of those numbers. 4 goes into both of those numbers. 8 goes into both of those numbers. And you can really, there's no, necessarily wrong way to do it. You can start by dividing both of them by the smallest factors. You could divide both by 2 and you get 4 over 8. And then you could do that again and you get 2 over 4, and then you could do it again and you get 1 over 2. Okay, you could also, I'm going to come over here on the left, you could also start by just dividing by the biggest factor, which is the most efficient way to do it. So divide both of these numbers by 8 and you get 1/2. And notice you get the same answer as when we divided by 2 and 2 and 2 over and over and over again. So as long as you're dividing by the same number, so the number you're dividing by is the exact same each time, and you do it until you can't do it anymore, until the only common factor is 1, then you should get to the same place regardless of which method you choose in terms of what number you're dividing by. The other option is to use your calculator. So you're going to be focusing a lot on probability here. So if reducing fractions is difficult for you and you want to rely a little bit more on your calculator for that part, you certainly can. I have a graphing calculator on my screen. I know a lot of you have a TI 30 or 34. I wish I had the software to show you that, but let me show you how to do it on graphing calculator, and then I'll talk you through how to do it on the other calculators. So if you had a fraction, for instance, 8 over 16, you're going to just put that in your calculator by using the division sign. Okay, there's also in the TI 30s and 34s, there's the N over D button, okay, and N stands for numerator, D stands for denominator, so you can press that button to enter in a fraction, and you can simplify by, let me just erase this to get more room, you can simplify by just pressing the simplify button, okay? And if you press that, it should simplify it for you. And then on the graphing calculator, if you want to simplify, so let's go back to the graphing calculator. We did 8 over 16, we got 0.5. If you hit the math button and then enter, so that way you're selecting that fraction option and then enter again, it gives you the reduced fraction. So let's just do that with another example. So let's say we had 13 over 52. That's a common fraction that you have with the card problem. So not 15, 13. So 13 divided by 52, enter. Okay, we get 0.25. Let's say you didn't know what fraction that was. You could hit the math button, enter, enter, and that'll give you 1/4. And again, if you have the TI 30 or 34 calculators, hit the N over D button. Okay, use your arrows to put in the 13 over the 52 and hit enter, and then use the simplify button, and that'll reduce it to the reduced fraction. So, okay, so now that we've got that out of the way, let's jump into the notes. So, and if you haven't downloaded these notes yet, I would suggest that you do that. I'll post them to Blackboard so that way you can follow along with me, and I would definitely suggest, pausing the video as you go to write things down. I think that's probably the best way to do it. But let's start with section 10.7. So, two events are mutually exclusive okay, if they cannot both occur at the same time. So if they cannot both occur at the same time, that's the most important part here. So for example, let's look at the deck of cards. So we've got this deck of cards picture, and I'm just going to label it here with what each card is. So J is Jack, Q is Queen, K is King, and then we have 13 hearts. That's this entire row. 13 diamonds. There's 13, these are called spades, and then there's 13 clubs, and that leaves 52 cards total, okay, in the deck. Oh, and then ace is going to be the A. The Jack, Queen, and the King, these are all called face cards in case that ever comes up in a problem. So let's look at some examples and then talk about what mutually exclusive means in terms of these examples. So with the first example, if we were to ask, what's the probability of drawing a 4 or drawing a 6? Those events are what we call mutually exclusive because it's impossible for a card to be both a 4 and a 6 at the same time. So I'm just going to write cannot both occur at the same time. There are no cards that are 4 and 6 together at the same time. The second example, drawing a 4 and drawing a heart, that example is not mutually exclusive. And the reason it's not mutually exclusive, if we look at the chart, there is a 4 of hearts. Okay, so there's a 4 of hearts, which means it is possible for both to occur at the same time on the same card. Okay, the reason why we're talking about events being mutually exclusive or not is because when we find the probability for them, it impacts how we do the probability, how we find the probability. So let's just jump into some examples, and we can always come back to the terminology when we look at these examples. Okay, so we've got this first, it's called Addition Rule 1, our book calls it. And it says for mutually exclusive events, these are events that cannot occur at the same time. And I'm just going to keep writing this over so it helps us learn what this is. We have this rule, and I'm going to circle, we have this formula, P, which stands for probability of A or B, is the probability of A plus the probability of B. What you really want to link together here is this or goes with the plus. So when you have a question that asks you for the probability of something or something else, you're going to want to use this addition rule. Okay, so let's look at this first example. So a restaurant has 3 pieces of apple pie, so I'm just going to write down. So we have 3 apple, they have 5 cherry, and they have 4 pumpkin. Find the probability that will either be cherry or pumpkin. So what's the probability of cherry or pumpkin? Now, first, let's think about cherry or pumpkin pie. Are these mutually exclusive? So can they happen at the same time? In this restaurant, it looks like no. They're going to either be cherry or they're going to be pumpkin. There isn't pie that is both cherry and pumpkin. So I'm going to say cherry and pumpkin are mutually exclusive, which means I can use my formula. So to find the probability of C or P, I'm going to take the probability of being cherry plus the probability of pumpkin. So, and to find those probabilities, I'm going to add up all the apple or all the pie and get a total. So we've got 12 total pies. So the probability that the pie is going to be cherry is 5 out of 12. Because there's 5 cherry out of 12. And then the probability of being pumpkin is going to be 4, since there's 4 pumpkin out of 12 total. Now, when you're doing probability, these denominators will almost always be the same, which is nice because when you're adding fractions, remember that the denominator just stays the same, and then you add the numerator. So 4 plus 5 is equal to 9, so the probability is 9/12. You can use your calculator to add fractions. I'll show you real quick how you do that. You do 5 divided by 12 plus 4 divided by 12, enter, and then you can hit math, enter, enter, and that gives you the reduced fraction. So 9/12 those numbers are both divisible by 3, and we end up getting 3 over 4 as an answer. Okay. Second example, so we draw a card from a standard deck of 52 cards. What's the probability of getting an ace or a queen? Now, it's not possible for a card to be both an ace and a queen at the same time. So ace and queen, we say, are mutually exclusive. They can't happen at the same time. So I'm going to write down the question. So probability of ace or queen, and then use the addition rule 1, is the probability of getting an ace plus the probability of getting a queen. So both of these are going to be out of 52 since there are 52 cards. I'm going to scroll up and look at my deck of cards just so I can get a visual. So it looks like we want, there are 4 aces and there are 4 queens. So I'm going to scroll back down, and it might be helpful just to print that off if you have a printer, or draw a quick diagram that you can just look at when you're doing your homework problems. So there are 4 aces and 4 queens. 4 plus 4 is 8, so there's an 8 out of 52 chance of getting an ace or a queen. And then that needs to be reduced. Both of those can be divisible by 4, or you can use your calculator, and so you get 2 out of 13 is the probability. Okay, so the next question, so we want to know what's the probability that a card, if we have a deck of cards, is either a club or a diamond or a heart. Okay, so these are all mutually exclusive. They cannot happen at the same time. There are 13 clubs, there are 13 diamonds, and there are 13 hearts. So we're going to take the probability of each one and just add those together. And when we add 13, 13, and 13, we get 39 out of 52. And when we reduce that, both of these are divisible by 13. So we get 3/4. And if you look at the deck of cards, you could also look at the deck of cards like this. You could look at it as there are 4 rows of suits, okay? And clubs, diamonds, and hearts. So clubs, diamonds, and hearts are 3 out of 4 of those rows. So it's another way to see the problem and see how you get the answer of 3/4. Okay, so those were all mutually exclusive examples. So now let's look at addition rule 2. So when events are not mutually exclusive, we're going to use a really similar rule. So again, I'm just going to highlight when you see this or here, we're going to add the probabilities of A and B together. But if they're not mutually exclusive, it means it's possible for them to occur at the same time. We have this extra layer here, this extra part of the formula where we subtract the probability of A and B. This just means we're just subtracting common elements, so they're not counted twice. Okay, so let's look at an example. So a single card is drawn from a standard deck of cards, so that means with 52 cards. Find the probability that is either a king or a club. Okay, so when we look at our deck of cards, so a king or a club, I'm going to go up here again. So a king or club, the first thing I'm going to do is I'm going to circle the kings and I'm going to circle the clubs. So it looks like, here, let me use a different color. So there are 4 kings and there are 13 clubs. So 4 kings, 13 clubs. Now, you might think, well, we'll just add those together and get 17. That's what we did before. We can't do that in this case because there's some overlap, and the overlap occurs here where we have this king of clubs. So as you're counting, one way to do this is even not use the formula at all. You can just count and make sure you're not double counting. So if I count, let me just go ahead and I'm just going to erase this so you can see me counting. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So one way is just to count and you get 16 out of 52. The other way is you can use the formula, Okay, so the probability of a king plus the probability of a club minus the probability of a king and club together. So there are 4 kings out of 52. There are 13 clubs out of 52, and if we added 13 and 4, we get 17. So notice that's too much because we counted and our answer should be 16 out of 52. So we have to subtract that one card, okay, the king of clubs, because that card is both a king and a club at the same time. So 4 plus 13 minus 1 is 16 out of 52. So we can use the formula, or you can count and just make sure you don't double count cards twice. And either one of those strategies will work. Okay, so let me just scroll down here. Whoops, scroll down a little too far. Okay, so you can go ahead and write that answer in there. Let's look at the dice example. So this is a picture of what it would look like, the sample space, if we rolled 2 dice. So imagine one was red and one was blue. For example, where you see this parentheses 1, 6, it means you rolled a 1 on the, actually, you know what, let me use a different color, and that way it'll look exactly what it should look like. So let's say you rolled a 1 on the red die, and you rolled a 6 on the blue die. That's what that means, okay? So let's go ahead and look at the question. So we want to know, what's the probability of getting doubles or a sum of 6? Okay, so are these mutually exclusive? So is it possible for these both to happen at the same time? So can you get 2 of the same numbers on the die and also get a sum of 6? And yes, you can. The 3 and the 3. Those are doubles, and it also gives you the sum of 6. So I'm going to use the formula probability of A plus probability of B minus probability of A and B. And transferring that to this card example, we're going to say the probability of getting a double plus the probability of getting a sum of 6 minus the probability of getting a double and sum of 6. Okay, so let's use the formula first, and then we'll just count, and I'll show you how you could do it both ways. So doubles. So let's count the doubles here. It looks like there are 1, 2, 3, 4, 5, 6 doubles out of 36 choices. A sum of 6. So sum of 6 is when you add them together and you get 6. So 5 plus 1 is 6. 4 plus 2 is 6. 3 plus 3, 2 plus 4, 1 plus 5. So these are all sum of 6. So 1, 2, 3, 4, 5 of those. Okay, and then we saw before there is one example, one outcome that's both a double and a sum of 6. So I'm going to subtract that one because I don't want to double count. And now I'm just going to add those numerators. So 6 plus 5 minus 1 equals 5 over 36. Okay, so that's my answer. The other way that you could do it is you could just count these and make sure you don't double count. So 1, let me use a different color. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, you know what? I wrote down that answer wrong. Sorry. We should get 10 over 36, and that's what we get over here. Actually, 6 plus 5. I said the wrong thing. 6 plus 5 minus 1. That should be 10 over 36. I was jumping to the reduced version. If you reduce 10 over 36, both of those are reducible. They're both divisible by 2, so we end up getting 5 over 18. Okay, but you can see that we did it 2 different ways. I would just pick the way that works for you. If you're given a chart in the problem like this and you can easily count, then feel free to totally just skip, the formula. It's fine. Or if you like the formula, then stick with the formula and don't bother counting. I think, either one works. I don't think you have to necessarily do both. All right, so let's look at the next example. So there's quite a few questions in the homework where you have a chart like this. So it says in the hospital, there are 8 nurses, 5 physicians. Okay, so it goes through all the different numbers of each. Let me just jump to the question. So if a staff person is selected, find the probability that the subject is a nurse or a male. So probability of nurse, oh, let me try that again. Nurse or male. Okay, so let's go ahead And let's just look at the chart and not use the formula and see what that would look like. So it looks like there's a total of 13 people. So I know my probability is going to be out of 13. Now let's look at all of the different numbers that are associated with being a nurse or a male. So it looks like there are 7 female nurses, 1 male nurse. So those numbers are all nurses. And then there are this number right here is also a male. So I could just look at the chart and count 7 plus 1 plus 2 because those are all the numbers associated with either being a nurse or a male. So nurses go this way, males go down this way. Notice I'm not double counting that 1. I don't want to count it twice. So we end up getting 10 over 13. So that's one way to do it. Okay, the other way is to use the formula. So I could say probability of being a nurse plus probability of being a male minus the probability of being a male and a nurse at the same time. Okay, so it looks like, and if you want, this would be the place where you could use the totals. So it looks like there are 8 nurses. So this is 8 over 13 plus there are 3 males, so 3 out of 13. Now if we add 8 and 3, that gives us 11, which is too much. That's not the answer we just got. And that's because we end up, when we do it this way, if we add the 8 and 3 together, then we end up double counting this 1 here in the middle, so the male nurses. So we need to subtract that out. So in our formula, we have to subtract the number of male nurses, so that's 1 over 13. So 8 plus 3 minus 1 is 10 over 13, and that's not reducible, so that's going to be our final answer. So some of the questions in Connect, you'll have these total columns, and sometimes you won't. So you just have to, it's going to depend on the problem. So just pay attention to the headings and whether or not the numbers represent total or if they're actually categories. Okay, so let's move on to section 10.8, which has to do with multiplication rules and conditional probability. So multiplication, so far we've had to add. So anytime you have a question that says, that has the word or, almost always you're going to have to add. In this case, we're going to talk about when you would use multiplication, and that's if you want to find the probability of what are called consecutive events. Another way to say consecutive might be multi-stage. For example, like if you pick 3 cards out of a deck. So far we've only picked 1 card out of a deck and you're asked, okay, is it a queen or a 4, for example. Now we're going to look at experiments that ask you questions like, okay, you picked 3 cards in a row. What's the probability that you get a queen and a 7 and another 7 in a row? And when you have 2 events that you're being asked about, they're considered independent if A occurring has no effect on the probability of B occurring. An example might be if you roll a die and you get a 6, okay, and then you roll a second die and get a 3. Rolling whatever you roll on the first die does not affect the probability of what you get on the second. Another type of, well, I guess the other part here is if the events are not independent, then they're considered dependent. Okay, which means that the outcome of the first event does have some effect on the second. For example, if you draw a card from a deck of cards and you do not put it back. So let's say you have a deck of cards in your hand, you pick up a card and you set that card aside, you don't put it back in the deck, and then you want to know the probability of picking something on the second draw. Well, when you take that first card and you set it aside on the desk beside you and you don't replace it, that's affecting the probability now, because instead of 52 cards in your hand, now you only have 51. So whenever you do not replace something, so I'm just going to write a note, this is without replacement, we say those are dependent events. If the problem says with replacement, meaning you replace the card or the ball or whatever you're taking out, then the events are independent, since we're basically getting the experiment back to normal before we do that second pick. Okay, so let's look at some examples so that these terms and concepts make a little bit more sense. So for multiplication rule 1. Basically what this says is that if you want to know if we have two events A and B, the probability that they both occur at the same time, so and you're going to multiply the probabilities of the individual events together. So let's look at an example. You flip a coin and then you roll a die. Okay? What's the probability of getting a heads on the coin and then, okay, a 4 on the die? So this is a multi-stage or consecutive experiment because you're doing one thing, okay, you're rolling a coin and then you're flipping a coin and then you're rolling a die. So we're going to take the probability of heads times the probability of getting a 4. Okay, so the probability of getting a heads on the coin is 1/2 because there's one head and two choices. And we're going to multiply that by the probability of getting a 4 on a die. Our choices for a die are 1, 2, 3, 4, 5, and 6. So the probability that you get a 4 is 1 out of 6. And then we're going to multiply those together. So let's talk about how to multiply fractions. You're going to multiply the numerator, or the top, times the top. So 1 times 1 is 1. And then the bottom denominator, 2 times 6 is 12. And then you're going to want to reduce if you can. You can also use the calculator. So you can use the parentheses and you can just enter 1 divided sign 2. Whoops, not 22, 2. Okay, times parentheses 1 divided by 6. You get a decimal and then hit math, enter, enter. And you get the 1/12. If you have a TI-30 or a 34, you're going to want to use the N over D button. And you're going to press 1/2 times 1/6 using the N over D button for both of these fractions and hit enter. And then it will give you your answer. It should give you your answer as a fraction. And then if it needs to be reduced, remember to use that simplify key there. Or even better, just do it by hand. But definitely don't hesitate to use your calculator as a resource if, fractions are a weak area for you because you want to focus more on the probability if that's the case. Okay, so let's look at the next example. So as part of a psychology experiment, we have some colored balls picked from an urn. The urn has 3 red balls, 2 green, and 5 white. Okay, a ball is selected, its color is noted, then it's replaced. This is really important. So when you are reading these problems, make sure you pay close attention to whether or not you put the ball back. Then a second ball is selected and its color is noted. Find the probability of each of these. So 2 green balls, that's like saying what's the probability of getting a green and then another green. Okay, so we're going to use our probability a multiplication rule and we're just going to multiply those probabilities together. So before I find those probabilities, I'm going to add up all of the different colors and I get 10 total. So that way I can figure out the probabilities. So probability of green is going to be 2/10 times 2/10. Here you can multiply straight across. You can also cross cancel if you want. So 2 and 10 are divisible both by 2. It really just depends on how you want to do your fraction. So I'm just going to be consistent with what I did before to keep it simple. 2 times 2 is 4. 10 times 10 is 100. And then I'm going to reduce, and that reduces to 1 out of 25. Okay, next example, what's the probability of selecting a green and then a white? So I'm going to multiply green times the probability of the white. So we just found out the probability of green is 2 out of 10. The probability of white is 5 out of 10. And I multiply straight across. 2 times 5 is 10. 10 times 10 is 100. Those are both divisible by 10. So I can reduce those and get 1/10. Okay. Last example, what's the probability of selecting a red and then a green? So the probability of a red, we're going to multiply that by the probability of green. So there are 3 reds out of 10, and there are 2 greens out of 10. 3 times 2 is 6. 10 times 10 is 100. Okay, and that also reduces. Both of those are divisible by 2. So we end up getting 3 out of 50 as our answer. Okay, now again, really important, this problem, oh, that was way bigger than I thought it was going to be. Let me see if I can do this instead. This part where it says then it is not replaced, that's the most important part, one of the most important parts of this problem, because otherwise it would affect our answers. And we'll do another one where it's not replaced later. Okay, so let's look at the next example. So we've got the, it's a deck of cards question, and we want to know what's the probability of getting a king, and then a king, and then a king. So king, and king, and king. So I'm going to take the probability of a king times the probability of a king times the probability of the king. And it's really important here. They said in the problem it is replaced before the next card is drawn. So these probabilities are all going to be out of 52 since there are 52 cards in a deck and there are 4 kings. So they're all going to be 4 out of 52. So the chance that you pick a king the first time is 4 out of 52. You put that card back. It's still 4 out of 52 the next time because you're putting the card back. So you're restoring the card deck to where it was when you began. So all of these are going to be 4 over 52. Now for these, definitely you could use a calculator. So you have a couple of options here. I just want to point out if you leave these 4 out of 52 and you multiply these across, you're going to get a really big number. One thing that you could do is reduce the fractions first. So 4 out of 52, those are both divisible. Those are both divisible by 4. You could reduce that to 1 over 13 before you multiply, and then it makes your numbers a little bit easier to deal with, but I'll show you how you could do either. So reducing it to 1 over 13, you're going to get 1 times 1 times 1 gives you 1. 13 times 13 times 13 gives you 2,197. So that's your answer, 1 over 2,197. If you had done it the other way, let me just show you. So 4 out of 52, 52 times 4 out of 52 times 4 out of 52, okay, you get a really, really small number. That's what that e to the negative 4 means. It's scientific notation. Let me just see if I can change that to a fraction. Okay, it does reduce it for me. I know sometimes with the smaller calculators, another strategy is to multiply the 4s on the top. So 4 times 4 times 4, and you get 64 on the top. And then 52 times 52 times 52 on the bottom, and you get 140,608. And again, you're going to have to reduce that. So you would you could use your calculator to reduce that. Or like I said, I think it's easier just to reduce those fractions before you multiply. It's a little bit less work. Okay, so let's look at the next one. So what's the probability of 3 clubs? So club, and then another club, and then another club. So we're going to multiply those all together, those probabilities. So there are 13 clubs out of 52, and 13 clubs out of 52 times 13 clubs out of 52. Again, if you can reduce those fractions first, it's helpful. So 13 over 52 reduces to 1/4. 1/4 times 1/4 times 1/4 is way easier to multiply. So 1 times 1 times 1 is 1. 4 times 4 times 4 is 64, and 1 over 64 is the answer. Okay, so we're going to move on, and again, feel free, you should pause the video at any of these points here so you can write down and maybe even, replay examples if you need to see it again. But we're going to move on and talk about the multiplication rule with large samples. So in this example, it says, according to the Gallup poll in 2007, 47% of parents in America with children under 18 feel frequent stress. So 47%. I'm just going to write down feel stress. I like to do this with word problems. Just kind of write down the important information. If 3 parents are chosen randomly, find the probability that all 3 will say they feel frequent stress. So what this means is probability that they will feel, the first person will feel stress, and then the second one will feel stress, and then the third person chosen will feel stress. Okay, so it means we have to multiply those individual probabilities together. Well, there's a 47% chance of each person feeling stress. which is 0.47 as a decimal because you move the decimal 2 spots to the left. And so we're just going to multiply 0.47 by itself 3 times. And we're going to get 0.104. Notice I just want to point out 0.47 times itself 3 times. You can use an exponent, okay? That's correct. What's not correct is doing 0.47 times 3. That does not work. That's 0.47 plus 0.47 plus 0.47. So you don't want to say 0.47 times 3. You can say 0.47 raised to the third power if you want to do a shortcut in your calculator, okay? So let's go through, let's look at a multiplication rule number 2. So multiplication rule number 2, I'm just going to erase this a little bit so we can see here. When we have these two events, A and B, if they are dependent, meaning the probability of the one affects the probability of the other, then we have this formula, which is pretty similar as compared to multiplication rule 1. When you see that and, we're still going to multiply, but notice the second part, probability of B given that A has already occurred. All this means is that we're going to tweak, okay, the second fraction to reflect that A has already occurred. And let me show you what I mean by that. So let's look at this example. So we have 25 plasma TVs. 3 are defective. If 2 TVs are chosen at random, find the probability that both of them are defective. And it says the first TV is not replaced after it's tested. So if it's not replaced, that means they're dependent events. Okay, and that means we're going to have to find the probability of the first one being defective and the second one being defective. So let's think about that first TV. So if there are 25 TVs total, okay, and 3 of them are defective, there's a 3 out of 25 chance. Whoops, I shouldn't have wrote 52, 25. It's hard to write and talk at the same time. So there's a 3 out of 25 chance that that first TV that you pick is going to be defective. Now, let's say, so we pick that first TV and we set it aside and it's not replaced, okay? Now how many TVs do we have? Well, now after we pick a TV, now we only have 24 TVs left over. So that's what I mean by tweak that second fraction. We've lost a TV because we didn't replace it. How many are now defective? Well, there was 3, but we picked a defective TV the first time, so now there are only 2 defective TVs, okay? So we started with 3 out of 25, and now we're left with 2 out of 24. And then we're still going to multiply those and use our multiplication rule. So 3 times 2 is 6, 25 times 24 is 600. Both are divisible by 6, and you end up getting 1 over 100 for an answer. Now, sometimes I know people will ask, well, do you always just reduce it by 1? Sometimes, but not always. And I think it just depends on the problem. Sometimes the denominator will change and the numerator, like in this example. Sometimes you'll just have the denominator change. It just depends on the problem. So this next example hopefully will help a little bit because it gives some examples of both scenarios. So this first one asks, what's the probability of getting 3 jacks? So that's probability of jack and then a jack and then another jack, okay? But this time we are not replacing cards when we take them out. So there are 52 cards in the deck to start with, okay? There are 4 jacks. We take that first jack out, okay? So this first jack, we take it out and we set it aside. So we start with 52. And 4 jacks, we put it aside. Now there are only 51 left and total, and there are 3 jacks left because we picked one that first time. So the second fraction is going to be 3 out of 51. And then this third fraction is going to be 2 out of 50 since we're down another jack. So notice the numerator reduced each time by 1, the denominator reduced because we were being asked about picking a jack and then a jack and then another jack. So the jacks reduced each time. And so if we reduce each of those fractions individually, we get 1 out of 13 times 1 out of 17 times 1 out of 25. And if we multiply those together, we get 1 out of 5,525. Okay. This next one wants to know what's the probability of getting an ace and then a king and then a queen in that order. And again, we're not replacing the cards after we pick one out. So the probability of getting an ace is this first one. We have 52 cards in the deck and 4 are aces. Okay. We set that card aside, so there's 51 cards left. What's the chance that you get a king? Well, we picked an ace the first time, so there are still 4 kings in the deck. So we're not going to reduce the numerator at all in this question. The next one, queen, we have 50 now, and there are still 4 queens in the deck because we haven't picked a queen yet. So the numerators are all going to stay 4, but the denominators are going to reduce. So let's go ahead and reduce any fractions that we can. So 4 out of 52 reduces to 1 out of 13. 4 over 51 cannot reduce, and 4 out of 50 is going to reduce to 2 over 25. And then we're going to multiply all those numerators and get 8, and multiply all the denominators and get 16,575, and that's going to be our answer. Okay, the next one, probability of getting a club, then a spade, and then a heart in that order. Really similar problem. So we start with 52 cards, 13 of them are clubs. Then we're left with 51 cards because we put that first card aside, and there are 13 spades. Now we're left with 50 cards, and there are 13 hearts. Okay, and so we're going to reduce any that we can. So 13 out of 52 reduces to 1/4. 13 over 51 cannot reduce, and then 13 over 50. Oops, looks like a 3. It should be 13 over 50 can't reduce. So I'm going to multiply the numerators and get 169, multiply the denominators and get 10,200, and that's going to be my answer. Okay, and last but not least, the probability of getting all 3 clubs. So a club and then a club and then a club. So I first start out with 13 out of 52 clubs. I take a club out, so now I have 12 clubs and 51 total. And then my third card, I now have 11 clubs and then 50. So the numerators are going to repeat when you have a repeat of what you're asking for. The denominators will always reduce if you're picking any type of card and you're not replacing cards. Okay, so I'm going to reduce any that I can. So I get 1 out of 4 times 4 out of 17 times 11 out of 50. Now you can multiply those numerators. I am going to just do a quick cancellation though. I notice that I've got the 4s here on the diagonal. You can reduce those by dividing both of those by 4 and you get 1. So 1 times 11 gives you 11 on the top. 1 times 17 times 50 gives you 850 on the bottom. And again, you can certainly use your calculator from the very beginning and just do 13 out of 52 times 12 out of 51 times 11 out of 50, and then you can do math, enter, enter, and get 11 out of 850. With the smaller calculators, you can use the N over D button and multiply those, and then use the simplify key. Okay, so last but not least, let's talk about conditional probability. So there's a couple different ways. Well, let's actually first talk about what conditional probability is, and then I'll talk about how we can approach the problems. So conditional probability is a probability question that often uses the phrase given that. So if we're being asked a probability of the second event occurring given that the first has already occurred. So we have this situation that we know is true. what happens is it narrows down our sample space a little bit, and it changes the way we calculate the probability. The way that we write conditional probability, so the way we write, what's the probability of event B occurring given that A has already occurred, we write it like this. So P of B given A. So this vertical line just means given that, or it is known that. Okay, there is a formula for this, okay, and the formula is right here. I would highly recommend just thinking about how to do the problem rather than using the formula, but I will also tell you in words what this means in case you like the formula. This top part just means the intersection, so remember when you learned about sets A and B, so if we think about A and B, the intersection between the two, what they both have in common. In probability of A, this is kind of like our condition, okay? So let's look at this first example. So I'm going to show you how to do it both ways, and then I'm going to do the next example just by thinking about it, okay? So method one, I'm just going to say method one. The first thing we're going to do is we're going to shrink our sample space. And you're going to do that by looking to the part of the question that comes after the word given. So look after the word given. So let's read the question. So what's the probability of getting an A given that you get a letter grade higher than a D? Okay, so if our original choices are A, B, C, D, and F, or incomplete, those are our grade choices. This says given that you get a letter grade higher than D. That means you absolutely know that you get a letter grade higher than D. Then I'm going to cross off D, F, and I because those aren't even possible. So I'm eliminating those. I'm shrinking my sample space and saying, okay, we know given my grade is higher than D, so my only choices are A, B, and C, which means my denominator is now going to be 3 because there's only 3 choices. And next, we're going to find the probability. So what is the probability of getting an A? Well, there's one A out of 3 choices, so my probability is 1/3. Method 2, okay, is to use the formula. So the formula here would be, we're going to do the probability of getting an A given that my grade is higher than a D. So I'm going to find the probability of getting an A and a grade higher than a D and divide that by the probability of getting an A. So the probability of getting an A, if my choices are A, B, C, D, F, and incomplete, is 1 out of 6. Okay. The probability of a letter grade higher than D is an A, B, or C, so that's 3 out of 6, or 1/2, okay? And so now I'm going to put it all together. So the probability of getting a grade that's higher, probability of getting an A and a grade that's higher than D at the same time would be 1/6, okay, divided by 1/2. Oops. And you could use your calculator at this point, or you could write it horizontally. So 1/6 divided by 1/2 is the same thing. Let me just scroll down here. I'm running out of room. Is the same thing as 1/6 times 2 over 1. So you get 2/6, which is the same thing as 1/3. Okay, I think it makes way more sense to use method 1 where we just shrink down the sample space rather than use the formula, but I did want to just show you how to do that in case you're interested. So I'm going to do one last example. I know this video is long. but I want to make sure to get through it all. I'll do this one last example, and I am going to think about this instead of using the formula. So we've got this table here, and I'm just going to jump right to the question. So the question asks, find the probability that a home got its power from a hydroelectric source given, okay, so this is conditional, that it didn't come from fossil fuels. So the first thing I'm going to do is I'm going to narrow down my sample space. So to find my probability, so I'm trying to find the probability, actually, you know what, let me just write it like this. The probability that the home got its power from a hydroelectric source given that it didn't come from fossil fuels. Okay, to find my denominator, what I'm going to do is I'm going to look at the given part. What's the probability that it's hydroelectric given that it didn't come from fossil fuels? So I'm going to circle, I'm going to cross off the fossil fuels, and I'm just going to add these guys together. If I add those together, so 807 plus 257.1 plus 168.1, those are the only numbers that I'm concerned about, okay? So when I add those up, I get 1232.2, okay? Given that, so just looking at the ones that didn't come from fossil fuels, what's the chance that it's hydroelectric? So that first part, that goes on the top. So if you're a visual person, the part that comes after given, that's your denominator. The part that comes before the given, the word given, that's going to be your numerator. So the hydroelectric, that's this number right here. So 257.1, that's going to go on the top. Now, in a question like this, like on Connect, it would just say to round probably to 3 decimal places. So you would just divide those two numbers. So 257.1 divided by, whoops, 257.1 divided by, and we're going to add all those up, parentheses, 807 plus 257.1 plus 168.1, end parentheses, okay, and we're left with this decimal rounded to 3. Let's round to 3 decimals. We get 0.209, and that's going to be your answer. So I would highly recommend just doing it like this. Again, really paying close attention to when you see that word given. A red flag should go up anytime you see a problem where you see that word given, or if we know that is another phrase that you'll see, or it's known that. And then the part that comes after the given, okay, that's going to be your denominator. Okay, those were the numbers that I added here. And the part that comes before the given, so hydroelectric source, that's going to be your numerator. So you find the hydroelectric and that goes on the numerator. So hope that helps. Let me know if you have any questions.